Hey everyone, good to see, well, at least lots of familiar names, if not many familiar faces. How's everybody doing?
Pretty good. How are you?
Good, how are you?
I'm doing good, thanks for asking. Um, Announcements, there is the final kappa 14 is up and ready for your consumption. I think it's only 14 questions. We should get through some of what you need to answer those questions today. So you can start that over the weekend. That will be due next Thursday at the usual time. There is, normally we'd be running into finals week, and I think Monday would be the last day of classes, but they haven't really organized it like a finals week. So I'm just treating next week like a normal week. We'll have class on Monday and Wednesday. There'll be normal kappa due Thursday, and we'll just do our last midterm on Friday. Thank you for those who did the reflective writing assignment today. I looked through some of those, although I didn't have a chance to grade them. That looked good. If you haven't done them, you should go through and do them as soon as you can, any of the ones that you're missing. Okay. That was all I needed to say. Let's get right to it. Yay. Oh, good. This is working. I was worried that it would not. All right. So we've done some cool special relativity things. But there's actually a lot more to it. We've done the weird space-time diagram and some of the paradoxes and talked about how to do some problems and solve some simple special relativity problems. Today we're going to talk about some other related topics. So, for instance, we know that if you have two different observers, they will not agree on necessarily the lengths of things, so delta x, and they will not necessarily agree on delta t's, right? Two observers on different reference frames will observe different delta x's and different delta t's depending on how fast they're moving relative to one another. So the question is there some sort of space and time-like quantity that is conserved no matter what reference frame you're in? Is there some delta x or delta t-like thing that we can write down that all observers, no matter what the reference frame, will agree on? And the answer is yes. And this becomes rather exciting because these, as the Minute Physics video said, if you can find things that are the same no matter what reference frame you're in, you're maybe learning something fundamental about the important things in the universe, right? And so what is that thing? It's called the space-time interval. So let's just put the question in your notes. What quantity related to space and time differences, delta x's and t's, is conserved, I should say not even conserved, is identical, does not vary, let's say that. Between frames. It's not delta x, obviously. It's not delta t, obviously. What is it? We call it the space-time interval. Space-time interval. Okay, and what do we mean by the space-time interval? Well, let's define it. We call it delta s, and we define it to be square root of delta x squared plus delta y squared plus delta z squared plus c times delta t squared, all square rooted. So note, what have we got here, right? This is the first three of these quantities, of course, are just the regular three spatial coordinate axes, right? So what are we talking about delta S? We're talking about the two events that happen in space-time, right? Two events on some space-time diagram. They'll have, each one of them will have a specific X, Y, Z, and T value, right? So you have one of them over here and one of them over here, and maybe they happen in different times. So you can take the X difference in X between those, the difference in Y's between those, the difference in Z coordinate between those, and the difference in time between those, plug them in this equation, and calculate a quantity called delta S, right? So this is some interval between two events in space-time. And the claim is, oh, and I messed it up. Sorry, I totally messed up this equation. There's some very important part that I got wrong. This plus is not a plus at all. This is a minus. If you have to cross out this in your notes, put a big X through it and write it again, do that. This is a minus sign and not a plus sign. So let's take this. What would this be if we didn't even have the delta T term in there?
That'd just be the distance from the origin.
Well, not even from the origin, right? If you've got 2 points in space, the difference in their X positions and Y positions and Z positions, you square all those quantities and you take the square root. That is the physical distance between those 2 points as measured by you, right, in your frame, right? Now we know that two reference frames won't agree, though, on just this part, right? Because we'll measure different delta X's if that's the direction we're moving in, right? And so this won't agree. But if you add this time, notice that there's a time thing in here. This time thing in here with a negative sign, then everybody does agree on this thing. So some notes. One, the first three are just the normal spatial dimensions. Spatial with a C, I think. I don't know. We would call this, if we were just doing this, right, this would be like a delta R. The square root of delta X squared plus delta Y squared plus delta Z squared would be kind of like the total, basically the distance between those two objects, the physical distance between those two objects. The time term, of course, because it has a C, as it has to if you're going to be adding or subtracting them, also has units of distance. And so delta S has the units, same units as distance. It's going to be in meters or something. Note the sign on the CT term is negative. So you might have heard throughout your academic career as you were studying physics that space-time is a thing, that time is nothing more than one of, an extension of the other three spatial dimensions. This is actually what people are talking about when they say things like that. There is a fundamental physical quantity that is invariant for all reference frames called space-time that involves the T term, the time term in some fundamental way that everybody agrees on. And that is in some ways a more true definition of a difference between two events that happen in time than just the physical distance between them. It is a better representation of what that actual separation between those two events is. And it's weird that this thing is negative, right? It comes in with the opposite sign. So everyone agrees on the delta S between two events, no matter what frame they're in. So that everyone agrees on delta S, no matter what the frame. So actually, you get some interesting things. Because of this negative sign, it's possible for this term to be bigger than these three terms combined. In which case you've got a negative, this whole term will be negative, in which case you're taking the square root of a negative number, which, you know, if you were in middle school, you would say that's impossible, but you're all advanced math students now, and you may even realize that that's not a problem anymore. It just becomes an imaginary number. And imaginary numbers work the same as regular numbers. They just happen to have a little I at the end of them. So that's okay. If delta S is imaginary, meaning that C delta T squared is greater than delta X squared plus delta Y squared plus delta Z squared, then we say the displacement is time-like. It is possible, what do we mean by that? It is possible for an observer to witness the two events at the same place. And by that, I mean delta R equals 0. If delta S is real, then it is space-like. And you can probably guess it is possible for an observer to see them happen at the same time. Is it possible for an observer to see events occur at the same time? So for delta T to be equal 0 for that particular observer. And if delta S is 0, meaning C delta T squared is exactly the same as delta X squared plus delta Y squared plus delta Z squared, then we call that a light-like interval. And these intervals cannot be given a proper time, length, or time. No proper length or time. There is no proper reference frame for observing those two events. These things happen for events that fall along the C line, right? If you have two, here is your XCT plane, Minkowski diagram. If you have two events, I drew a dotted line, you can't really see the two events. If you have two events that occur along the C line, those two will have a delta S equals 0, and you can't even really talk about the length or time between them. Okay, so that's fun. We're not gonna have much practice calculating delta S quantities, but it is useful to know that there is such a thing called a space-time interval, and that it is the thing that is invariant. It is the quantity that everybody will agree on, no matter what their, between two events, no matter what their reference rate. Okay, let's do more practical things, at least for the homework. Velocity transformations. Okay, so we have spent a lot of time thinking about how two different observers witness events happening in their particular reference frames, and how to transform between their two perspectives. What we haven't thought about yet is how do different observers in different reference frames observe a third velocity moving with respect to both of the first two, right? So we now have three velocities to deal with. We've got the two reference frame, the velocity, the v that we've defined to be the velocity between our two original reference frames. And then we've got a third object that is moving in some other direction with some other velocity relative to the first two. And we need to figure out how these two observers are going to agree or disagree about what the velocity of the third one is and how they're going to relate them. So let's say v is still going to be the velocity between the frames. We're still only going to be talking about two reference frames, and v will be the velocity between them. And let's call ux, comma uy, comma uz the velocity of any other object in the x and y and z components, in this case in the unprimed frame. And in the primed frame, we could call these u prime x, u prime y, and u prime z the velocity of the same object in the primed frame. Okay. This is not as simple as just multiplying or dividing by gamma, which is usually what you get when you're doing delta t's or delta x's. So if you want to see the derivation, you can see the text. I'm going to kind of go through it a little bit, but if you want the full derivation, you go to the text. So what is ux in terms of u prime x? In other words, if observer, again, we've got the same situation as before, right? We've got one reference frame that is moving with respect to the other at some velocity v. And that unprimed observer, the original reference frame, sees a third object moving through its reference frame with velocity ux. Okay, so ux is going to be the x velocity of that third object in the unprimed observer's reference frame. Well, we know that this is dx dt. And we know what dx dt are in terms of, at least we know what these are. We can do Lorentz transformation for x. We can do a Lorentz transformation for t. We know what those are in terms of x prime and t prime. So let's just take the derivatives of those, right? So this is going to be the derivative of the Lorentz transformation. Let me propagate the d's in and save one step. This is going to be gamma times dx prime plus v times dt prime. So every time I have a variable, meaning x and t, velocity is not changing, so gamma doesn't change and v doesn't change, then I'm moving the d's to be in front of those variables. So, and the t on the bottom, I have a gamma also. I have a dt prime plus v over c squared times dx prime, right? This is just plugging in the Lorentz transform for x and the Lorentz transform for t and propagating the d's through to all the variables. Okay, let's multiply and divide both sides, top and bottom, by dt prime. We get gamma times, oh, the gammas actually cancel out, so those we don't have to worry about anymore. We get dx prime dt prime plus v on the top, and we get 1 plus v over c squared times dx prime dt prime on the bottom, right? Just taking 1 over dt on the top and 1 over dt on the bottom and canceling out the gammas. This, though, what is dx prime dt prime? That is u prime x. That is the velocity s of that object as seen in the primed frame, right? That has to be u prime x plus v divided by 1 plus u prime x v over c squared. And this is the equation, right? If you want to know if the prime observer is observing at a particular velocity in x, and you want to know what it's going to look for like for the unprimed observer, you have everything you need to know. You can plug it into that equation. Interestingly, uy is not just u prime y, sadly, right? You have a dy dt. Y and y prime are the same, but t and t prime are not the same. And so u prime y is not equal to uy. So we have to do the whole thing out. This is just dy prime on the top. That's easy, but we still have a gamma dt prime plus v dx prime dt over c squared. Oh, that's not the dt, that's just a d. V over c squared, right? Notice that this is an x. Why is this an x?
I think that was in our formula before because it's traveling in the x direction.
Right? That's exactly right, because we have defined the v to be in the x direction, right? And so the dt only changes in the x direction. And so this becomes, this is just in the dt, the definition for the Runge transform of dt, but it is x because v is in the x direction, right? Because that's how we define the x direction. Okay. This is once you get all this stuff pointed out, again, you can divide both sides, top and bottom, by dt prime. I'm not going to do the whole thing, but you get u prime y divided by gamma times 1 plus u prime x, interestingly, v over c squared. And you can probably, I won't even do it, it's the same thing for uz, u prime z, uz is u prime z divided by gamma times 1 plus u prime x, v over c squared. So these are your boxable equations. You'll need these for some problems, and this makes homework up. This is a z. Great. Let's do an example. You are standing here. There's you. And you see rocket A moving by you at a certain speed. So you see rocket A moving by at beta equals 0.8. So this guy is moving at 0.8 c. Okay. Rocket A sees B moving at beta equals 0.8, right? So rocket A sees rocket B move by at 0.8 c. What do you observe for rocket B? What is B's velocity in your frame? In other words, what do you see for the velocity of rocket B? You can see why this no longer works, right? Normally, you would naively say, well, if I see rocket A going by at 0.8 and rocket A sees rocket B going by at 0.8, then it must be that I see rocket B going by at 1.6, right? And that cannot be, because we can't see rocket B going faster than the speed of light. So this is where all of our velocity addition things break down, because they can't add in the same way they normally did. So this gets confusing. The hard part of these equations is always figuring out what u is, what u prime is, what u is, and what v is, right? You've got two velocities, 0.8 and 0.8. One of them is, you know, and they are the combination of v or u prime. And your job is to figure out which one of those they are. If you plug it, if you get it wrong and you plug it in, you're going to get a value that doesn't make any sense, right? What do you know for what we observe, what we will observe for B, right? It has to be less than the speed of light, and it has to be greater than what?
0.8.
Right. It can't be moving any slower than rocket A. We know that rocket B is moving faster than rocket A in the x direction. So it has to be a number between 0.8 and 1. If you plug in numbers and you get a number that's negative, or if you get a number that's greater than 1 or less than 0.8, you know you've done something wrong. Okay. So again, with all physics problems, hopefully you have enough intuition about the physics to know about what the answer should be before you plug your numbers in. Always a good idea to be doing this as you go along. Okay, so what is V in this particular case? What are the two reference frames in this particular case?
V will be rocket A.
U and the rocket A. And that's right. And how do you know that's right? It's because you're given two velocities, and those velocities are given in those two frames. One of the frames is your reference frame. That's the first one, beta 0.8. And the second one is from A's perspective, and that is also beta equals 0.8. So you're given two frames. You're given a velocity in two frames. Those have to be your two frames. And the velocity between those two frames has to be V, okay? So if we call, well, it's going to depend on which we call the primed and which we call the unprimed. It's going to make sense to call us the unprimed observer in this particular case, and this the primed observer, because they're moving positive. A is moving positive relative to us. That's really the only reason. So in this case, V is 0.8. Otherwise, it would be negative 0.8. 0.8c, right? This is the velocity between the frames. And the frames are what we see and what A sees. Those are our two frames. And 0.8 is the difference between those two frames, 0.8c. Okay. What is the other? Um, 0.8c.
Is that U prime?
Yes, it is. That is the velocity of the object as seen from the primed reference frame, right? If you're the unprimed frame, A is seen B in the, that's a velocity as seen in the primed frame. So that has to be U prime X. We're not even dealing with Y and Z. Let's forget about Y and Z. We're not even going to think about those really. This is traveling just in the X direction, so we don't have to worry about it. This is U prime X. Great. We now have everything we need to do to figure this problem out. We want UX, and we have a whole bunch of U primes. We can do that. We know, we wrote this down before. It's not on my board anymore, but it's in your notes. This is U prime X plus V divided by 1 plus U prime X V over C squared. And we can add these up, right? The top is what we naively expect, 0.8c plus 0.8c. U prime X is 0.8c, V is 0.8c. This is, if we weren't for special relativity, this is what we would expect to have happen. This business down below is the adjustment that we have to make because of how we have to add these things in special relativity. Okay, this becomes, we have a 1 plus U prime X is 0.8c, V is 0.8c, and we divide by C squared.
Isn't there a gamma on the bottom?
There's only a gamma on the Y's and Z's. There is no gamma on the X because they canceled out.
Okay.
Yep. Okay, so this becomes 1.6c on the top. On the bottom, we get, C's actually all cancel out. That's fun. 0.8 times 0.8 is 0.64. This becomes 1 plus 1 is 1.64. This becomes divided by 1.64. So this, again, is just your scaling term to get this back down to a normal thing that will be less than 1, less than c. Divide 1.6 by 1.64, and you get 0.976 c, which is a number that is larger than 0.8 and smaller than 1. And it kind of even makes sense, right? You know that this B has to be moving really fast. It can't be moving quite the speed of light, but it's going to be getting pretty close. And sure enough, it got pretty close. Do another example? Let's. Okay, now let's say and observe, you are here now. And let's say rocket A is moving towards you in this direction. And rocket B is moving towards you in the other direction. And let's say you observe this rocket going at plus 0.8 c, and this rocket going also at 0.8 c in the other direction. So we want to know what the velocity of rocket B will be from A's perspective.
Would it be useful to make our frame the prime frame in this example?
Yes. Well, let's perhaps let me wrap my brain around this for a second. I think I'm ready to go. So what do we want? We want UB, the velocity of rocket B from A's perspective. You can do this, and you can set this to be the prime frame, or you can set this to be the prime frame. It doesn't really matter. But again, these are the two reference frames we're interested in. We're given two U's in this frame, and we want a U in this frame. So these have to be the two U's that we are. So we could certainly start with this person as the prime frame and make this the unprimed frame. Or we could do it the other way. We could make this the unprimed frame and make this the prime frame. Let's stick with this being the prime frame, right? What is V then? Sorry. No. Let's stick with us being the prime frame. You can do it in either direction, but I've done it from this direction, and I think it's going to be instructive to do this. So let's stick with us, you being the primed frame. What is V? So you are the prime, you are the unprimed frame. Yeah, this gets confusing. I was using prime as the reference, the primed reference, but what I mean was the unprimed frame. So let's say you are the unprimed frame. I think I said that completely backwards a bunch of times. If you are the unprimed frame, what is V?
Would it be negative 0.8 because it looks like you're moving toward A?
Right.
Because from A's perspective, A is stationary, so you're moving towards A.
That's right. If we made A the unprimed frame, then it would be negative because we would be moving towards it. Since we are the unprimed frame, the velocity is the primed frame's velocity relative to the unprimed frame's velocity, right? We always draw this with the unprimed frame, right? And then the primed frame moving to the plus X direction. And that's still what we have here. The unprimed is us, And even though it's got a negative x position, it's still moving in the plus x direction. So for the unprimed frame, the primed frame is moving in the plus x direction, and that is v. So it's actually positive 0.8 c. Does that make sense?
Yeah, I was just flipping things.
Exactly, which I've done already several times in this particular problem. What is the other 0.8 c?
That would just be u of x then.
That's right. That's really negative u of x, since it's traveling in the negative x direction. That is a velocity as measured by an observer in the unprimed frame, and so that is an unprimed ux. So ux is negative 0.8 c, right? And our job now is to figure out what u prime x is. This is the primed frame, and so we want to know what this velocity is from the primed frame observer. Yep. Oh, I forgot the negative sign. This is negative 0.8 c. Yep. Okay. Now, I didn't write down the equations for u prime x as a function of u. That's going to be important. Let me do it now. In order to, so we have ux as a function of u prime. We don't have u prime x as a function of x. Again, these are weird equations. You cannot simply take them, the u as a function of u prime, solve that equation for u prime and call it the u prime function of x, because they are fundamentally different. I see your clocks running slow and you see my clocks running slow. You can't just take my equation for your clocks, turn it around, and make it your equation for my clocks, because that will make it so that you see my clocks running fast. They are fundamentally different equations in going from mine to your clock and your to my clock. That was something I didn't emphasize before and probably should have, right? Let's just think about that example before we finish this problem, right? We know that what a delta t equals delta t prime over gamma or something like that. You can't just turn this around and say delta t prime equals delta t over gamma. It's not true. This shows me that your clocks run slow. What shows you that my clocks run slow? Well, that's delta t prime equals delta t over gamma, right? These are both fundamentally true equations that are fundamentally opposite, right? You can't go from one to the other. They're different equations. One applies for me observing your clocks, and one applies for you observing my clocks. It's the same kind of thing here. The equations we wrote down are what I see, what the unprimed observer sees for the primed observer's velocities. Now we have to write an equation that reverses those. Okay, so just be wary with all of these equations. You can't just turn them around and do algebra. You have to use the right equation to go from the right place to the right place. Another reason why these all get very weird. Okay, let's just write them down. U prime x. So all you do, you switch the prime and unprimed and reverse the signs, right? That's what has to happen, right? The only thing that's different between me and you is that I see you moving at a positive x velocity, and observer A sees me moving at a negative x velocity. So all you have to do is change the prime and unprime and change the sign of the v terms. Okay, so this becomes ux minus v divided by 1 minus ux v over c squared. And u prime y is equal to uy divided by gamma times 1 minus ux v over c squared. And the same with z, you just change the y's to z's. Okay, so let's do the calculation. I'm out of space, but that's okay. I think I can do it up here. I don't need much space because this becomes pretty simple. U prime x, again, and that's what we want. We have ux, and we want to find out u prime x. We want to know the velocity of this in the primed frame's reference frame. Okay, so this is u prime x, which is negative 0.8 c, minus v, which is 0.8 c, again, this is going to be you know you're doing this right if this gives you what you would expect without special relativity, right? If I see this moving in this direction at 0.8c and this moving in this direction at 0.8c, I would expect naively this observer to see negative 1.6c for that rocket, right? This should be your sanity check. If this doesn't check out just based on normal velocity additions, then you're doing something wrong. Okay, and this on the bottom is 1 minus ux, which is negative 0.8c. So this is minus negative 0.8c times v, which is 0.8c over c squared. And this, you'll see, becomes negative 1.6c divided by, this becomes exactly the same calculation as before. The c's and the c squareds cancel. You get 0.8 times 0.8, which is 0.64. Negative of a negative is a positive. 1 plus 0.64 is 1.64. And look what you get. The exact same numbers we had before, except the negative sign. 1.6 divided by 1.64, you get negative 0.976c, which shouldn't actually be surprising, because this is, in fact, a very similar problem to what we were looking at before. In fact, yeah, this is sort of like the middle observer, right? Remember our last situation. We had U over here and A moving by at 0.8 and B moving by at 0.8 as seen from B, right? If you take the same picture from A's perspective, it looks like this frame is moving in this direction and this frame is moving in this direction, both at 0.8c. It's exactly the same problem as this one, just seen from a different, you put yourself in the perspective of rocket A instead of the opposite. So we just switched which were the prime and the unprimed frame. Really, that's all we did. We solved the same problem switching which was the prime and the unprime, and we got basically the same result. That make sense? That's a lot, but you'll have some other chances to work on this stuff on homework. Questions? Are we lost? It's tough to teach over Zoom because I have no feedback. Usually I have some blank stares or some furrowed brows or some expressions to let me know when everybody's lost, but I'm just gonna have to take your word for it now.
I think it makes sense. It's a little mind-bending to think about all the different frames of reference, but
it is. And that's always the hardest part about these questions. You know, the formulas are easy to implement. You just have to figure out what V and UX, you know, what it is that you have and put them into the proper context. That's the hard part about these problems always.
Yeah, the fact that this is basically the same problem we just did twice, I think is very intuitively helpful to understand the way that the equations relate to each other.
Good. That was my hope. Excellent. Okay, we've got 7 more minutes left in this class. Let's do one more topic, which is somewhat simpler than velocity transformations. And that is relativistic Doppler effect. Okay, so you might know the Doppler effect. If you have an object that's moving towards you or away from you, waves that are being generated or emanating from that object will be blue shifted if they're moving towards you, and red shifted if it's moving away from you, right? And so so this is the non-relativistic. This is what you would learn in a high school physics class or a introductory astronomy class. These are the non-relativistic equations. F observed, the frequency of a wave that's observed by a moving platform is equal to F naught times 1 minus beta over 1 plus beta. Oh, I'm sorry, that is the relativistic Doppler effect. Sorry, wrote the wrong equation down. I'm at the wrong part of my notes. This is the normal Doppler. I'm going to write that equation down, but that is the regular Doppler. The normal Doppler is delta F equals V over C times F naught, where F naught is the rest frequency. In other words, the frequency that a wave would have, if the object that's emitting it were at rest relative to you. Delta F is just F minus F naught. F is the observed frequency. In other words, F naught is what you would observe for the frequency if that object were at rest at you. This is the actual frequency you observed for the object not at rest. And V is the radial velocity. So radial velocity means component of the velocity that's along your line of sight, right? So it's only the component. This is different than a normal velocity through space. Radial velocity, if you're standing here and you have some object moving at some dynamic velocity, it is only the component of that velocity that's along your line of sight, right? Either towards you or away from you. Motion perpendicular to line of sight does not affect the frequency of the waves or the wavelength of those waves at all. You'll also see this written V over C equals lambda obs minus lambda rest divided by lambda rest. Where again, these are the wavelengths, the observed wavelengths, and the wavelength of this wave would have. Usually, we're talking about light waves here, right? So the wavelength of that light wave would have if the object were at rest relative to you, and the wavelength that you actually observe it at in real life. And this is the velocity as a function of C with C. There is a convention that I've only seen broken a couple of times, which is that positive radial velocity is away and negative radial velocity is towards. So this would be a negative radial velocity. If the object were moving away and this would be a positive radial velocity. Okay. That's just a convention. Okay, well, how we do this relativistic? This doesn't work in relativistic form. What is the relativistic equation? Well, I just wrote it down. F obs equals F naught times 1 minus beta over 1 plus beta. Lambda obs equals lambda naught times square root of 1 minus beta over 1 plus beta. They're cast differently. We don't talk about betas here. We talk about betas here, but they're just they relate the same quantities. Okay, here's a warning. If you go and look this equation up in Thornton and Rex, I know many of you probably don't even have this textbook, so it wasn't an issue, but I want to warn you because this is important. The plus and minus signs on these equations will be reversed. The plus will be on top and the minus will be on the bottom. Thornton and Rex is wrong. Thornton and Rex has defined beta exactly the opposite as convention dictates. They have defined positive beta towards and negative beta away, which is what flips the sign on all of these, right? I mean, maybe there's some branch of physics that does it backwards, but that's completely backwards. As an astronomer, we're right on this. We talk about radial velocities all the time. Positive is definitely away and negative is definitely towards. And if you're talking about relativistic Doppler effects, it's really the astronomers who are having the game. So we're right. Anyway, these are the equations that you're going to need for homeworks this week. Know that Thornton and Rex is wrong because they define beta in the opposite direction. Okay, with my 1 minute left, let's do a quick example. Beta equals 0.9, an object moving away from 9/10 the speed of light, and let's say wavelength is 656 nanometers, which is, as you probably all know by now, an important wavelength. This is H alpha. This is the wavelength at which H alpha appears. So H alpha photons are heading towards us. but the object itself is moving away from us at 9/10 the speed of light, where are we going to actually see these photons? They're not going to be at 656 anymore. So where are they going to be? Lambda obs equals lambda naught, which is 656, times, let's just do it, 656 nanometers, times the square root of 1 plus 0.9 divided by 1. Uh-oh. Now my notes are not making sense because I've done this the other way.
I was actually going to ask, how is it possible for those two equations to be the same if, like, frequency is what is like the inverse of lambda, with c is like the constant?
Yeah, that may be a problem. I don't think that's a problem. The real problem is in my notes I have a plus on the bottom, on the top here, and a minus on the bottom. So it's possible that these are wrong and this is right. Crap, I'm gonna have to look this up now. My notes are giving me conflicting numbers on this. So it's possible that these signs are flipped. But anyway, let's do this with plus on the bottom and top and minus on the bottom now. You get, this is square root of 1.656 nanometers times 1.9 on the top and 0.1 on the bottom, which is also wrong in my notes. Geez, this is bad. And I hope this is right, 656 nanometers times, I think that this is going to be some large number, which you take the square root, you get 4.359, which is 2859 nanometers. That's certainly going in the right direction. So the point is, if you were to use the regular, normal, non-relativistic Doppler effect, there's no, since objects can never go faster than the speed of light, wavelengths can never be more than doubled. But with the relativistics, as you get closer and closer to the speed of light, these wavelengths get shifted. Oh, I didn't even put that. These wavelengths get shifted longer and longer and longer. And this is 4 times larger than the rest wavelength, right? This is way out in the infrared, mid-infrared, so 2.8 microns. So this is a major difference between the relativistic Doppler effect and the non-relativistic Doppler effect. I will come back in the beginning of class next time. We'll fix this negative sign issue, which seems to be apparent between these two formula. And also, I will investigate the question about these two being different. I don't think they are, but I will double check that. So apologies for snafus at the end of this class. Have an excellent weekend. I'll see you on Monday.
You too. See ya.
Thank you.